All right, welcome to this tutorial session. Okay, today we just want to talk about tutorial sheet 11. Okay, on how to go about those questions in that tutorial sheet 11. Okay, so tutorial sheet 11 is actually about acids and bases. Okay, acid and bases. How to find the pH, how to find the pOH, the conjugate bases, the conjugate acids. What else? We have buffer solutions. Okay, so that's what we wanted to talk about specifically in this session. Okay, so we'll go straight into it with question 1 there. Okay, so the first question there is saying write the conjugate acid for the following Bronsted base. Okay, so for you to write the conjugate acid, then you must understand what it is. Okay, you must know how to define it. Whether it's a conjugate base, conjugate acid, you must know first how to define it. Then it will be very easy for you to write a conjugate base, conjugate acid for anything. Okay, so that's what we want to do. Okay, so what is the definition? So here I wrote for you. Okay, so a conjugate acid is actually a species or a compound, okay, formed by the addition of a proton. Okay, by a proton, we just simply means an hydrogen ion. Okay, we are adding to something, we are adding a hydrogen ion. Then whatever will be formed after adding an hydrogen ion to that thing, that's the conjugate acid. Okay, so here we are given this guy, and then they are telling us to find the conjugate acid of this guy. Okay, so how do you find the conjugate acid? You just add a proton there, which is hydrogen ions. Okay, so when I add this hydrogen to this, okay, what will be formed? Okay, you can see that this one here has a minus charge, which is just 1. Okay, and then here has a positive charge, which is just 1. So meaning that when I add positive plus negative, just going to give me 0, right? So it's going to be 1, a neutral compound that I'm going to form. Okay, and then here I have 2 hydrogens plus this hydrogen is going to be 3. Okay, so no wonder here whatever I got there, that was our conjugate acid. Okay, so the hydrogens were 2, we add another hydrogen, it becomes 3, and then the charge it was minus 1 plus 1. When they combine, they form a neutral one. Okay, so minus 1 plus 1, we know that it's what? It's 0. Okay, so no wonder this thing here is neutral, and this guy here is going to be acting as our conjugate acid. Okay, all right, we go to number 2. Number 2, what does it say? They're saying complete the following chemical reaction, highlighting the conjugate base, the conjugate acid base pairs, okay, and give their respective K expression. Okay, so a K expression has come again. Do you remember from the chemical equilibrium tutorial, right? Okay, so for us to complete this reaction, it means we just have to write, because this guy here is acting as an acid because there's presence of H there, right? And then this guy here is acting as the base, right? So for this acid, it's going to lose this hydrogen to the base, okay? And this base is going to gain the hydrogen from the acid, okay? So when this hydrogen here is lost, okay? We know that the hydrogen always carries a positive charge, right? Okay, so when this hydrogen is lost here, it goes with its positive charge, okay? So what you're going to remain with is just S4, okay? And then here there was minus 1 initially, but because one of the positives has gone, okay? So it means this will become now a minus 2, all right? I hope I haven't lost anyone. Then plus, and then here, this guy here is receiving H plus, right? Okay, so if it receives H plus, it's going to be H, okay, PO4, okay, and then this H plus has come with a positive, remember? So we have 3 minus plus that 1, okay, so this means will become 2 minus like that. Okay, so here, this guy here is obtained by losing, okay, losing an electron, a proton, I mean. So if you lose a proton like that, whatever you get here will be your conjugate base, okay? Then remember for the conjugate acid, how we defined it, you add a proton there, okay? So it means this guy here is our conjugate acid. You've seen that these things are nice, right? Okay, so from the acid, you get your conjugate base. From your base, you get your conjugate acid, just like that. Okay, it's like it's magic, something like that. Okay, so that's what happens there, and it's the same thing that I did here. Add that plus that, okay? This guy has lost a hydrogen like that, okay? It has become this, and then this guy here has gained a hydrogen like that, and it has become that, okay? And then the question said indicate the conjugate acid base pairs, okay? So we can say that this guy here will just go with that one, okay? No wonder I paired them here, okay? This is the acid conjugate base. And then that guy there will go with that guy, okay? This is the base, this is the conjugate acid, like that. All right, and then the K expression, that should be very simple for us all, okay? Because we went through it in the tutorial sheet for chemical equilibrium. Okay, so it means the K value, you are just going to write the concentration of this, divided by concentration of that, concentration of that. It's exactly what I wrote there, okay? So that's how you answer number 2. Then we can go to number 3. Then let's check the question. Okay, so number 3 says what? Okay, number 3 says what? Okay. Right. Okay, so number 3, they are saying write the conjugate bases for each of the following. Okay, so what did we say conjugate base is? Okay, something that is obtained after losing a proton, right? Okay, so let's go to our solution. To our solutions, we check it out. So a conjugate base is a species formed after an acid donates a proton, or in other words, after it loses a proton, right? Okay, so we have this compound here. If this compound loses a proton, it means the hydrogens will reduce from 3 there, they'll become 2. And then since this one had a positive charge, which is just 1, it means that that hydrogen that is leaving, okay, is getting the charge. You can see it there, right? Okay, so it means that one just remains as a neutral compound like that. So this is our conjugate base in this case, and then plus those hydrogen ions, okay? Then in the second one there, a hydrogen leaves, okay? The hydrogen carries a positive charge like that, okay? Means here there were 4, 1 has left, they become 3. And then it was neutral, but the positive one has left, meaning it will become a minus. So the conjugate base there is that one, okay? Any questions? Feel free, my inbox is always open. Okay, we go to question 4 now. Okay, let's read question 4. So question 4, what are they saying? They're saying calculate the hydrogen ions, okay, and hydroxide ions concentration as required for each of the following solutions at 25 degrees Celsius, and indicate whether the solution is neutral, acidic, or it's basic. So we have those two there, A and we have B, okay? So here I've been given the concentration of hydrogen ions, then they have been given the concentration of hydroxide ions. So let's calculate and see. Okay, so before we even calculate, I have to mention that the pH and the pOH are just measures of acidity and basicity respectively. Okay, so the pH there measures acidity, then the pOH measured basicity. Okay, so the pH runs from 1 all the way up to what? 14. Okay, in fact from 0. Okay, 0 all the way up to 14, even the pOH from 0 all the way up to 14. Okay, so if you have a pH, okay, so the breaking point is 7 there, even there it's 7. So if you have a pH less than 7, you say that thing is acidic. Okay, then if you have a pH greater than 7, you say it's basic. Then when we come to the pOH here, so this is the pOH there, then there is just the pH. When we come to the pOH there, okay, pOH, it's actually the opposite. Okay, so if you have a pOH that is less than 7, okay, you say that wait, what am I looking for here? Okay, yeah. So if you have a pOH there that is less than 7, you say acidic. Then if you have a pOH that is greater than 7, you say it's basic there. All right. Have I said the correct thing? No. It must be the opposite, yeah. And I'll doubting myself. Okay, so when you are dealing with a pOH, let me repeat. If you have a pOH that is less than 7, then it means it's basic. Okay. Then if you have the pOH that is greater than 7, it means it's acidic. Okay. So they are opposite. If it's pH, less acidic, greater basic. If it's pOH, less basic, greater acidic, right? So we are not confused there. And then there are a series of formulas. Okay. There are a series of formulas that you need to be aware of in order to carry out these calculations. Okay. There are a series of formulas that you have to know in order to carry out these reactions. Okay, so the first one there is that pH is given by the negative log of the concentration of what? Hydrogen ions. Then pOH is given by the negative log of the concentration of hydrogen, hydroxide ions, I mean, okay? Then another thing that you should do is, you should know, is that when you add the pH and the pOH, they should always give you what? 14, okay? Okay, so remember the question said we find the pH, okay? We find the pOH, we find the concentration of hydrogen ions, and then we find the concentration of OH there. Okay, so here on A, we are given the concentration of hydrogen ions, so no need to calculate it, but we are going to use it to calculate all these, okay, using the formulas above there. Okay, so we have the concentration of H plus, okay, we can simply find our pH using that formula there, okay? So pH is equals to negative log, the concentration of hydrogen ions there. Then you simply punch into your calculator. So log of that number is going to give you minus 4.4444. And then you have that negative again outside. So negative by negative, you get your pH as that, okay? Then we have to make a conclusion here. Since the pH is less than 7, you can say it's 4.44. Since the pH is less than 7, then this solution is what? Acidic, right? Okay, then R, after we found the pH, we can use it to find the pOH. Okay, so we know that pH here, we know that pH plus pOH is just equals to 14. And we want to find our pOH. It means this pH goes the other side and it becomes a minus there. And your pOH will just simply be that. Okay, and then from the pOH, we know that we can find the concentration of the hydroxide ions. Okay, so pOH is equals to minus log of OH ions. Okay, so borrowing the information that we have from mathematics, okay, we know that we can convert a log, okay, from a log to an exponential, right? Okay, so if I have a log of base A, then here I have x is equals to b, okay? So I can convert this log to an exponential, okay? And how do I convert that? I use this mnemonic, BAM, okay? I use this mnemonic, BAM, not what you're thinking of. Okay, but I use this mnemonic. What does it mean? Okay, it means that base to the power answer is equals to what is in the middle. Okay, so this guy, the b there, is our answer, and then the a there is our base, and then the x there is what is in the middle. Okay, so bam, right? So base to the power answer is equals to what is in the middle, meaning a to the power b is equals to x. Okay, so this is the principle that we're going to use here. Okay, so know that the log that they use when calculating these pHs, it always has a base 10 there. I even showed it here. Okay, if you want, you cannot show it, but there's always a base 10. Okay, so base to the power answer, this one is the answer now, right? Is equals to what is in the middle there. Okay, so the concentration of OH is just equals to 10 to the power minus pOH here. Okay, someone might ask, where is the minus pOH when this is positive? Okay, before you get the bump here, you first divide both sides by a negative. So this becomes negative, and then that becomes positive like that. Then you can get your bump now. So base to the power answer is equals to what is in the middle. No wonder that expression there. Then just replace with your pOH there, where we found there. So minus 9.56 there. You punch into your calculator, you'll be able to find the concentration of our OH there. Okay, amazing. All right, let's go to B. Okay, so B, we are also going to use the same approach. So on B, we are given the concentration of the hydroxide ions. Okay, so we are first going to calculate our pOH there. So pOH is equals to minus log of the concentration of the OH ions. We replace it there, punch it to your calculator to give you negative 5.89. Multiplied by the negative outside, you're going to get 5.89. Okay, so remember the rule. We said that when the pH is less than 7, then the solution is what? Basic. Okay, so that's the conclusion there. The pH is less than 7. No, not the pH, I mean the pOH is less than 7. So the solution is basic. If we are using the pH there and it's less than 7, we would have said it's acidic, right? Okay, so don't get confused. So now that we've calculated our pOH, we can calculate our pH, okay? All right, okay, we can calculate our pH. Okay, so pH plus pOH is equals to 14. We know the value of this guy. We get our pH as that, okay? Then from the value of the pH, we can calculate the concentration of the H plus, okay? So I put the value of the pH there, 8.11 is equals to minus log 10 concentration of H plus. I divide both sides by negative. The negative goes to the left. There it has no negative, okay? Then when you reach here, you apply our BAM, right? Our BAM base to the power answer is equals to what is in the mid. Okay, so the base is 10 to the power answer minus 8.11 is equals to the concentration of hydrogen ions there. Okay, so when we apply them into the formula and you punch that into your calculator, you're simply getting this as your answer. All right, so we move to the next question, which is question number 5. What is it saying? What does it have for us? Okay. Okay, so question number 5 says, calculate the values of the pH, pOH, H plus, OH for the following solutions at 25 degrees Celsius. Okay, so here we have given us a compound, not exactly the concentration of the H plus or the concentration of the OH. Okay, so it means here, before you do anything, you have first to calculate the what? The concentration of either the H plus or the OH minus, right? Okay, so we are going to do the same thing that we did on the previous question, but the only difference is that here we need to calculate the concentration of that H plus or the concentration of that OH minus. Okay, so how do we calculate that? We use the concept of ions in solutions, right? I'm sure you learned that. So let's look at how I did it. So question 5 there, we have been given 0.02 molar hydrochloric acid, okay? And we know that hydrochloric acid is a strong acid. So when I put it in water, it will dissociate complete, okay? So it will dissociate into hydrogen ions and chlorine ions, okay? So first, to find the molarity of this or the concentration, we simply multiply its coefficient with the concentration of the whole thing there. Okay. So in this reaction, we can see that the coefficient of this HCl is 1, even the H is 1, even the C is 1. Okay. So we're going to get that coefficient multiplied by the whole concentration that it has. So that's just 1 multiplied by that. You're going to get the same thing as your concentration of the what? The hydrogen ions, right? Okay. Then once you have the hydrogen ions, then it will be easy to calculate your pH. Once you calculate your pH, you can calculate your pOH. Okay. Then from your pOH, you can calculate the concentration of this H minus, right? Just like we did in the last previous question. Okay, so just substitute into this formula the concentration here. You're going to get your pH. Then for that pH, we know that pOH will just be equals to 14 minus pH. Okay. And then we'll get that as our pOH. And then to get our OH concentration, we're just saying 10 to the power minus pOH. Okay, so we know where this is coming from, right? Okay, so we had the pOH like that is equals to minus log concentration of pOH. Okay, then we said from this we can move to the exponential. Okay, so we're moving from that side to that side so that the formula becomes simple, right? Okay, so just put our pOH there on top with the minus, punch into the calculator, you're going to get this as a concentration of the OH, right? So there I write them down now, all of them, once I found them. Okay, so this is our concentration of H plus, pH, pOH, concentration of OH minus. Okay, so on B, we also do the same. Okay, but here there's something that I want you to notice. Okay, so this is barium hydroxide, right? So when you put barium hydroxide into water, it's going to dissociate into its ions, right? Okay, so the first one there will dissociate into barium 2 plus, and then plus, since we had the Ca2 here in front of this OH, this Ca2 follows and becomes that 2 in front there, and then the OH minus like that. Okay, so for us to find the concentration of this OH, okay, we're going to multiply this coefficient 2 multiplied by the whole lot of this concentration of barium hydroxide. Okay, so concentration of that is just 2, which is that 2 there, multiplied by the concentration of the barium hydroxide. Okay, so I'm going to get 7 to the power, 7 times 10 to the power negative 4 molar as my concentration of my OH minus. Okay, then once I have my OH minus, then it means it will be very simple for me to find all these others. So I start with the pOH, I use that formula, put into that formula, punch into your calculator, you're going to get this as our answer. Then since we have the pOH now here, we can use the pOH to calculate our pH. Okay, so pH is equals to 14 minus pOH, which is just 14 minus 3.16. You're going to get that as your pH. Then from your pH, we know we can calculate our concentration of ions, right? Okay, so from that formula that we had, like pH is equals to minus log of the concentration of H plus there. Okay, you turn this into a logarithmic graph. Okay, it's just be like that. Then you put your pH there, which is that number, and then punch into the calculator. You're going to get that as your concentration of hydrogen ions. Okay, then you can write them down there, all of them like that. Okay, yeah, so that's how you solve that. And then we go to number 6. Okay, let's read number 6. So number 6, they're saying what now? They're saying calculate the pH of 0.1 molar formic acid solution at 25 degrees Celsius. Okay, so formic acid, you have to notice that formic acid, later on I'll give you a table. Okay, I'll give you a table of these acids. You have to know that formic acid is a weak acid. Okay, so it means its dissociation is partially, okay, it does not ionize completely. Okay, you find that some hydrogen ions will separate from the acid while some will remain with the acid. Okay, so whenever you are given a weak acid, you have to be given a Ka value. Okay, Ka value is just the equilibrium constant of that acid. Okay, remember the K and the Kp. Okay, so when they say Ka, that's meaning the equilibrium constant of an acid. Or when they say okay, so when they say Ka, they just say equilibrium constant, okay, of an acid. And then also meet Kb, okay, it's just the equilibrium constant of a base. Okay, so don't be confused by those terms. Okay, so whenever you're given a weak base, weak acid, you need to know the Ka or the Kb. And these values are constant values. They were already calculated for us. We just get at place somewhere. Okay, so if you're writing a test or a quiz or an exam, they always give you that K value or that Kb value. Okay, but again, if you can manage to memorize them, just feel free to memorize them. Okay, so here we want to find the pH of that weak acid there. Okay, since it's weak and it does not ionize completely, we are going to use what we know as the ice table. Okay, so the ice table like that. Okay, so this I means initial concentration, then the C means the change in that concentration, and then the E means the equilibrium concentration. Okay, so we're going to use an ice table. Okay, so let me check what we did there. Okay, so an ice table looks something like that I wrote there. Okay, so we have been given the pH, and the Ka for formic acid is just that guy. Okay, so we don't calculate this value, you're just given. You can search on the internet, Google, anywhere. Okay, or you can check in your notes. So the Ka value for formic acid is that, and then the pH is that. Okay, here you're asking to calculate the pH of. Okay, I don't know why I wrote pH here. So here, this is the concentration, right? Yeah, so this is the concentration. Okay, so you can write concentration here, not pH. The pH is what we are looking for. Okay, yeah, the pH is what we are looking for there. Okay, so the concentration is that, the Ka is that, and then put whatever you have on the ice table. So formic acid has that formula. Okay, so you have to get familiar with these formulas for this weak acid. They just give you the name, and they expect you to know what it looks like as a formula. Okay, so formic acid has this formula. Okay, and when it dissociates, it will just lose this one hydrogen, and this other hydrogen will remain. Okay, so when it loses that hydrogen, you have these two forming like that. Okay. So now the ice table, what does it do? Okay, so remember the concentration that we had is that, right? For formic acid, right? So initially we had the concentration of formic acid as that. Okay, then the concentration of these guys were 0, 0. Okay, before it dissociated, we had nothing for these guys. Okay, before it was this formic acid dissociated, so we have 0 there, 0 there, and then they change. Okay, since this guy here, when the reaction happens, when the dissociations starts to happen, okay, it will be this concentration will be decreasing, right? Okay, because it's dissociating. So since it will be decreasing, we indicate it with a minus x there. That's the change. Okay, a change of magnitude x, because we don't know how much the change is, but we just know that we can represent it as the change in x, which is that minus x there that I'm putting. Okay, and then for these products that are forming now, their concentration they were 0, and then as the reaction goes, their concentration starts to increase, right? Okay, so this guy will increase by positive x, and then even that guy will increase by positive x. Okay, so what will be the equilibrium concentration? Now we are on the E. Okay, what will be the equilibrium concentration? You just combine these two. Okay, 0.1 to be minus or x, then here 0 plus x, x, 0 plus x, x. Okay, so these here x, x, and 0 minus x, they are our equilibrium concentrations. Okay, and we know that from our equilibrium concentrations, we can find the Ka value, or just the K value. Okay, so the K value has been given there, and then we have these equilibrium concentrations. Okay, so we have to put this equilibrium concentration to that formula. So Ka is equals to, remember the products there first, and then the reactants down there. Okay, so what is the value of this product? It will just x, value of that product, x, and then down there, what is the value of that reactant? 0.1 minus x. Okay, so now here you should pay attention. Okay, so now, depending on the value of the Ka that you have there, okay, sometimes you are dealing with bases, it will be the value of the Kv. Okay, immediately you notice that this value here is a very small, it's a small number. Okay, because 1.8 times 10 to the power minus 4 is a very small number, right? So if that number there, the Ka or the Kb, it's very small, okay, you conclude that if you have a number being added to x or being subtracted to x, it means the change will have no effect. Okay, the change will have no effect. So here I wrote, since this guy is small, okay, or it's small in value, okay, it means the 0.1 minus x will have no effect. Okay, it's the same as removing this x. Okay, it will just give you 0.1. Okay, why? Because the value there is so small. But if that value was big, say we had 1.8 times 10 to the power 5 there, okay, you can see that this number is very big. It means that x there will matter. But in this case, where this Ka is small, the x won't matter. So the 0.1 tends to just become 0.1. The 0.1 minus x will just tend to become the 0.1 there. Okay, so what we'll have on top there, x multiplied by x will be x squared. Then down there will just be 0.1. Then we have that guy there. So cross multiply, 1 multiplied by that, you get that. Then this guy multiplied by that, you get that. And remember, your aim is to find that x, because that x is the concentration of hydrogen and the concentration of that guy there. Okay, once we have the concentration of our hydrogen, then we can find our pH, right? That's the aim here. We want to find this pH. Okay, so let's proceed. So when you multiply that, you get that, and then you just want the x, so you square root both sides. The square goes, square root that side, and you're going to get that as your answer. Okay, then there you conclude. Therefore, this guy there since the X here equals to the concentration of hydrogen ions, is equal to the hydrogen ions concentration, right? And then once you have your hydrogen ions concentration, it will be very easy for you to find the pH. Just put it into that formula, punch on your calculator, you have your value for the what? For the pH there. Okay, so that's number 6. And then let's go to number 7. So number 7 says what now? They're saying a certain acid was found to have a pKa equal to 4.88. What is the value of the Ka of the acid? Okay, so this is very simple. Remember our pH, okay? So whenever you hear P something, okay, just know that P something will be equals to log the same something, okay? Okay, so pH was equals to minus log of concentration of hydrogen ions. It means this pKa here will just be equals to what? Minus log of the Ka there, okay? So every time you hear P something, just know that it's the minus log of that thing. Okay, so the pKa and the Ka, they are related by that formula there, okay? So in the question, we'll be given the pKa and we're being asked to find the Ka there, right? Okay, so how do you find your Ka? Okay, so this is the formula there. We can change that formula into exponential, okay? Remember I said the log that they use here always are the base 10 there, okay? So from this form here, we can convert it to our BAM. So base to the power answer is equals to what is in the middle, and what we get is that, okay? So it means the pKa there is just equals to 10 to the power minus pKa, okay? And the pKa, the value we have. So you put there, punch on your calculator, you're going to get this as your Ka value. Okay, we go to number 8. What's the question on 8 now? Okay, on 8, they're saying a certain base, HB, has this pKb value now, okay? Value of that. And then what is the Ka value for its conjugate acid, okay? So here, notice that we have been given the pKb, which is for a base, but here we've been asked for the Ka for the acid, okay? So how do you do that? So there's a formula that relates the pKa and the pKb, okay? So just like we have pH plus POH, okay, is equals to 14. It's the same principle. The pKa plus the pKb will always be equals to 14, okay? So since they have been given the pKb, we're going to use this formula here to help us find the pKa. And then after finding the pKa now, we can find our Ka, right? Okay, so that is our pKb, our pKa we don't know. So from that formula here, when we rearrange it, we see that pKa is just equals to 14 minus pKb. Okay, I substitute the values, I'm going to get that as my pKa, okay? And then from that, my pKa, I can calculate my Ka. So Ka is just equals to that, okay? Remember the formula we had, pKa, okay, is equals to minus log Ka there. Okay, so when you apply BAM here, you end up with that guy there, okay? So our K is just equals to 10 minus pKa. Put the value of the pKa there, and I'm going to get this as my Ka. Okay, right. Go to number 9. Okay, so let's see the question before you can see the solutions there. Okay. Okay, so number 9, what does it say? What does it say? So number 9, they're saying calculate the pH of a buffered solution. Oh, no. Number 9, they're saying, I was reading number 10, they're saying a 1.5 liter solutions contains 0.12 moles, okay, of that guy, okay? And then that is acetic acid, okay? That is acetic acid with that formula. So you have to get familiar, right? And then they're saying 0.12 moles of that, and then again 0.12 moles of that, okay? So this is sodium acetate. And then they're saying determine the pH of the buffered solution. Okay, so you have to know that a buffer solution is just simply a mixture of a weak acid, okay, with its conjugate base, okay, or a weak base with its conjugate acid, okay? What did I say? I said that a buffered solution is a mixture of a weak acid with its conjugate base or a weak base with its conjugate acid, okay? So in this case, we've been given acetic acid there with its conjugate base, which is sodium acetate, okay? So in a buffered solution, you're simply trying to resist change in pH, okay? All right, so we have moles of that and then moles of that. So it means these moles, we have to convert them into molarity, simply concentration, right? Okay, and then after we convert them into molarity, we have to know the K value of that weak acid, which is acetic acid, okay? Remember I said for weak acid, you always have to know the K value, okay? So you have to know the Ka value there, which I'll show you soon. Okay. And then how do you determine the pH of a perfect solution? You always use the HH formula. Okay. So the full name I'll show you. So the pH using the HH formula is just equals to, okay, the pKa plus, okay, log base over acid. Okay, so this base over acid, I'm talking about the concentration. Let me even put to my bars like that. Okay, so the concentration of the base on top, the concentration of acid down there. Okay, then if you want to find the pOH, you can also use this formula, the HH formula. Here where you have the pKa, since you're finding the pOH, which is for a base, you're going to have your pKb plus log, and then there, these things here will switch sides. Okay, since we're finding for the pOH and we have pKb there, the concentration of the acid will go on top, and then the concentration of the base will go down there. Okay, so that's what we have there. Okay, so these pKa values, the pKb values, they're always given. Okay, they're always given in your test or exams. They are always given. They are constant values. Okay, what you have to worry about is your concentration of the base, the concentration of the acid there to find your pH or your pOH. Okay, so in this question, we've been given the moles and the volume there. Okay, so using that volume and these moles, we can actually find the molarity of that and also the molarity of that, right? Yeah. Okay, let me erase some back up screen. Okay, so let's go to the solution then. Okay, so here the HH formula in full, it's known as the Henderson-Hasselbalch equation. Okay, in short, you can just say the HH equation, right? And it's given by that in terms of pH. Okay, so you have to know the Ka value for this acetic acid. So the Ka value for this acetic acid is just 1.8 times 10 to the power minus 5, okay, which is a constant value they have written. So we need to find the molarity of that guy there, and again the molarity of that. So I've been given the moles and the volume of those things. So we're just going to divide moles divided by volume, get the molarity, and then moles divided by volume and get the molarity, right? Okay, and then once you get the molarity there, this is for the acid and that is for the base, you go and put them into the formula, okay? So remember that this pKa there, okay, remember that the pKa is just equals to minus log of the Ka. Okay, so we replace now. So wherever there is pKa there, I replace with minus log of Ka there, then plus log. Then on top there, I'm going to put the concentration of the acid, the base, I mean. Then down, I'm going to put the concentration of the acid. We can see that this will give us 1, right? And then log 1 is just simply 0. Okay, log 1 is just simply 0. And then here I'll put minus outside. Then log this number there is going to give you minus 4.74. Negative times negative is going to give me this guy, plus 0 is the same thing. So that's our pH using the HH formula. Okay, I'm pretty sure even number 10 is on the HH formula. So let's look at it. Where's number 10? It's there. Okay, that's number 10. But let's read the question first. So number 10, they're saying what now? Okay. Number 10, they're saying calculate the pH of the buffered solution prepared by dissolving 21.5 grams of benzoic acid and 37.7 grams of sodium benzoate in 200 milliliter solution. Okay, so it's the same thing that we're going to do. Here we've been given a benzoic acid. Benzoic acid is 3. Okay, and then we have been given its conjugate base, which is just sodium benzoate. Okay, so we've been given the mass of that benzoic acid, mass of that sodium benzoate. Okay, so we know that if we know the formula, we can calculate its molar mass in the periodic table. And then we use that molar mass with the given mass to find the moles of that benzoic acid. Then after we find the moles, combine those moles with that volume to find the concentration. And then those molarities that we're going to find, we put them into the equation, okay? But remember, you have to know the Ka value for this benzoic acid, okay? So let's go and see what I did. So here we use the Hasselbalch equation. And then I was saying first calculate the moles of benzoic acid and sodium benzoate, and then calculate the molarity. Okay, so benzoic acid has that formula. You need to swatter this formula. And then sodium benzoate has that formula, because sometimes they just bring the names. Okay, so it's up to you to know the formula. So the mass of this benzoic acid will be given that, the mass of sodium benzoate will be given that. And then, I mean, this is the molar mass here. So the molar mass, you calculate from the periodic table. You add molar mass of hydrogen plus 7, the molar mass of carbon, plus 3 molar mass of hydrogen, plus 2 molar mass of oxygen. And you are simply getting roughly this value there as your molar mass. You do the same here. This is the mass you've been given. Then you find its molar mass from the formula. Okay. And we know that the volume is just 200 milliliters, which is the same as 0.2 liters when you divide this by 1,000. Okay, so let's find the moles. So moles of benzoic acid, mass over molar mass, we get that. Moles of sodium benzoate, mass over molar mass, we get that. Okay, and then now let's find the molarity. We know that the molarity or the concentration is just dividing the moles with the volume. Okay, so the volume is the same for both. So moles divided by the volume, I get my molarity. Moles divided by the volume, I get my molarity. Okay, so the sodium benzoate there is the conjugate base, and then the benzoic acid is the weak acid, right? Okay, and then now we apply this formula. Remember, the Ka for benzoic acid there is just that value there. Okay, that's that value. Yeah, this is the value there. It's given in test, so don't worry about it. It's a constant. So you get this guy, okay, and then you simply put. Remember here where I've put this guy, that's where we had pKa, right? Okay, so pKa is just minus log of the Ka. So the Ka is that value, I put it there, plus log. On top there, I put the concentration of the base, right? Down there, I put the concentration of the acid, okay? So when I divide these guys and then I apply the log, okay, or you can do direct log of, you put the brackets, 1 point whatever they are divided by that number, you get 0.42. Then this side, negative log of that number, you get 4.14, okay? Then when you add them, you're simply getting that as your pH. Okay, so we are done with tutorial sheet 11 on acid and bases, okay? So on acid and bases, make sure you know the HH formula, okay? And make sure you know what else. Okay, let me see from the question. Make sure you know how to find the conjugate base or how to find the conjugate acid, right? Okay, then know the formula for the pH, know the formula for the pOH, know how you can find the concentration of the H plus, okay, from the pH, know how to find the concentration of OH minus from the pOH. Then if you know those 4 things, then you're good to go, okay? And then know the relationship between the pKb and the pKa, okay? We said that the pKa plus, okay, the pKb should always equals to what? 14, okay? So don't forget this. And then another thing is the automation of water, okay? I don't know, we didn't have any question about water here, but you should know that when you multiply the Ka for the automation of water multiplied by the Kb for the automation of water, you get Kw like that, okay? So in case they give you Kb, okay, so this Kw is a constant value, which is 1 multiplied by 10 to the power minus 14, okay? So in case they give you Kb and they want you to find K, you can also use this formula, okay? You can also use this formula. Ka multiplied by Kb just equals to Kw, and Kw is that value, okay? So make sure you take note of that, and have a blessed day.